exam. So with that in mind, we're going to do a review today, which is going to help you for exam 3. And it's definitely going to be something that will help you as you get ready for your final exam as well. So if you think about all of the work that we've done this semester, we have covered a fair bit of ground. Within the first third of the semester, we looked at chapters 1 through 4. You can think of those as really the foundations of chemistry. And then in the middle of the semester, we took a look at gas laws, and then an introduction to thermochemistry and an introduction to quantum chemistry. And then in the last third of the semester, we really thought about how that quantum chemistry transferred into the way we organize electrons and we form bonds. And we looked at three-dimensional structures of molecules. And then the last part, chapter 10, was starting to think about phase changes, so how we move between physical states of matter. So if we think about that from a big picture view, we're going to zoom in and look at some specific types of problems. And I pulled some of these from exam 2 because I think they're really great examples of problems to review. And they were the problems that I noticed folks had some challenges with. And so I want to make sure that we touch base and resolve some misconceptions and think about some of the strategies that we can use to effectively solve these problems. So I hope you know by now that questions are always welcome. So if for some reason, as we're walking through these problems, there's something that doesn't make sense to you, please feel free to use the chat box or to unmute yourself and ask a question. I have specific ideas that I want to touch base on for these problems, but if there's something else that we haven't talked about that's going to be important for you to make sense of solving that problem, then please don't hesitate to ask. Your question is highly valuable and will improve the learning of everyone. So please don't hesitate to ask. At this point in time, I hope that you can think about these science practices the way you think about saying your ABCs. So your ABCs are really something that you could reiterate again and again because you said them so many times. That's the idea behind these science practices. You will be able to make sense of new knowledge, so even a problem that you've never seen before, because you understand how to use these practices. So don't fret, right? Seeing something that's brand new is totally common, right? That's what we do as scientists. We see something and make sense of that new information, and then we iterate the way we solve a problem if the first time we tried to make sense of it didn't work. And so we have these 4 practices that we use all the time when we're solving problems. And we're going to look today at some examples of how we do that. So before we leave, here's the big reminder. If there's anything that shows up again and again and again on exam 3, it is intermolecular forces. So please make sure that you have in your mind a distinction between intermolecular forces, that is the forces that are between molecules, and intramolecular forces, or the forces that are within molecules. That's going to be really important as we go forward because you're going to be asked to do something with your knowledge of intermolecular forces, and you'll be asked to differentiate between ionic bonds and covalent bonds based on your knowledge of intramolecular forces. So just a quick reminder, that's definitely something that we want to be attentive to because it's going to be something that's going to show up, and we'll use it again, not just this semester for our exams or final exam, but next semester in Chem 111, in organic chemistry, in biochemistry. This is one of the topics that's so transcendent that it shows up in marine science, in kinesiology, in biology. Essentially, it's a topic that touches all aspects of science that we might study. Okay. Good question. Yes, the review is a lot like the actual exam, indeed. So my point of going through these topics is to show you examples of problems that you are likely to encounter on your actual exam. So just like the practice exam is helpful because it gives you the types of questions that you would commonly expect to see, the problems that we're going over today are examples of problems that you should expect to see both on exam 3 and on the final exam. That's a great question. So with that in mind, let's take a look at this example. So we have to balance equations in many different types of problems. But here is an example of balancing equations that requires us to do 3 tasks. The first task is that we have to translate our words, so nickel chloride and sodium phosphate, we have to translate those words into symbols. And so if you think about what we studied early on in the semester, you had to be able to make sense of the names of molecules and then what their symbolic representation is. So that's one of the skills that you as a chemist need to be able to use. Then the next task is to be able to write a balanced equation using the correct products and the stoichiometry. So notice in this problem, you're only given the starting materials. You're not told the products. You are told that it's a double displacement reaction. So the next task is being able to take your starting materials and figure out what your products might be. And then the last task is being able to write the ionic equation and the net ionic equation. So that's what we're going to look at. And we're going to be able to identify the final, which is the precipitate or the product that's the result of that reaction. So each version of exam 2 had a question that was like this. You will see a question that is like this on exam 3 and potentially on your final exam. So here's an example. When we are first writing out this equation, we need to be able to think about a couple of things. So nickel and chloride. Well, I don't necessarily know off the top of my head what the charge is on nickel, but I'm confident that the charge on a chloride ion is -1. I know that because I can look at the periodic table at the second to last column, and I know that those have 7 valence electrons, so all they want is to gain 1 electron in order to have a noble gas configuration. That means that when I form an ion from fluoride, it's going to be a -1 charge. So if I know that chloride has a -1 charge, then I have to go and take a look at nickel. And if I'm looking at nickel in my periodic table, one of the things I'm going to notice is that nickel has the possibility of forming multiple types of charges, but I can tell based on its position that it's most likely to form the following. So if I look at my periodic table, and I find nickel on my periodic table, nickel is here. And so if it gives up 2 electrons, right, then it's going to be over here. And I know that iron ions are forming, so it makes sense that I would be able to form nickel plus 2 ions. So I'm going to start there and see if that will help me out. So Ni and Cl2, that's how I form nickel chloride. Then sodium phosphate is something that relies on my knowledge of polyatomic ions. So do I know that a phosphate has a -3 charge? That's a polyatomic ion that I might just need to know off the top of my head. And if I don't know that, it might be something that's worth writing down on my sheet of resources that I want to make sure I have with me and accessible. So PO4 3- means that I need to have 3 sodiums because sodium has a +1 charge. Now, the beautiful thing about this problem is that it tells you what happens next. The words double displacement reaction tells you that you're swapping. So that means that the nickel, instead of having an ionic bond with the chloride, instead is going to have ionic bonds with the phosphate. You're literally swapping the anions for each other. So in this case then, nickel now will have to have 3, and that means its charge has to change. Right? So nickel 3 and PO4, and then 6, right, NaCl. And so if I think about that then, when I'm writing out my balanced equation, part of what I then have to do is make sure that I actually have the right amount of atoms on each side. So let's take a look and check to make sure that that's the case. So if I have 3 nickel on the left, I have 3 nickels on the right. I have 2 PO4 on the left. Ooh, I only have 1 PO4 here. Right? So I might need to think about how else I could balance my equation. Right? So maybe what I need to do here is put a bracket around my phosphate. Right? If nickel is 2+ and this is 3, that would be, right, a 6 plus overall charge, so I'm okay there. Then put another bracket here and put a 2, then those cancel. So I want to make sure that I'm balancing. This is a great example of where I want to be attentive to how I balance my equation. Notice, right, this is a solid. It's going to form my precipitate. You might be wondering, well, how do I know that it's a solid? That, again, is going to be based on your solubility rules. If you don't have those handy, that might actually be something that you want to pull out as a resource for taking exam 3 in your final exam. Okay, so let's talk a little bit about forming or writing the complete ionic equations and net ionic equations. So if I'm thinking about how I write the complete ionic equation, that's where everything gets separated out as aqueous ions. So in this case, I have 3 nickel, I have 6 chloride, I have 6 sodium plus. Notice the charges are really important here. That's something that I'm going to be looking for when you're writing these out. In addition to the charges, right, we make sure that we're balanced. Our nickel 3 phosphate, so this should have a bracket and the number 2, then we're balanced. And then 6 Na plus and 6 Cl minus. Then our next task is to be able to cancel our spectator ions. So anything that is the same on the left as it is on the right, so in this case, 6 Cl minus and 6 Cl minus. And then the other piece that we want to be really attentive to is the fact that if, right, we have another spectator ion, in this case we have sodium, right? So here we cross out our 6 sodium plus and our 6 sodium plus there. So it's really easy to figure out then what our net ionic equation is if we've crossed out our spectator ions, because then anything that's remaining is what we're looking for. So again, the only thing that should be fixed here is that this should have a bracket and the number 2 next to it. So in your notes, make sure you make that change. I'll go ahead and fix these before I post them up to iLearn, but this should have a bracket and the number 2, and then we have an overall balanced equation because I have 2 phosphates here. So make sure that you have the bracket for phosphate here and the subscript 2. Then I know that nickel phosphate is my precipitate, and I know that that's a precipitate because I have a solid. So that's something I want to be attentive to. This balanced equation is something that, in this case, is a problem all by itself, and it asks you to do multiple things. But sometimes a balanced equation is something that we have to do in the process of solving another type of problem. And so a really great example of that is a question that showed up on your exam 2. So, yeah.
Going back to that last question, I just have a quick question about why Cl or chlorine on the left side for the second line. Why wouldn't it be 3Cl2? And then why doesn't nickel have a 2 plus charge?
So here, right, this Cl2, right, this is an ionic bond where when I put NiCl2 into water, it separates and becomes 1 nickel that has a 2 plus charge and 2 individual chloride ions that have negative charges. So in water, it completely separates. And because I have this AQ sign, I have 3 times 2, right, which gives me 6 chloride ions individually separated out in solution. So because it's an ion, it completely separates. And then I think you had another question, Zoe. Can you ask the other question again?
What about the 3 nickel plus? Would it be 3 nickel plus or 3 Ni2 plus?
It's 3 Ni2 plus, and that's the reason why I think we need the brackets here and the subscript 2 for the phosphate, because then it's a balanced equation.
Okay, and that's on the left side too?
On the left side, yes, that is correct.
Thank you.
Because there's the number 2 there. Yep, you got it. On the left side are 2 here, right? So you don't need the brackets and the 2 for the phosphate here because it's in front. Do you see that? There's a green 2. So I have 6 total sodiums, right? And I just have 2 phosphates.
Okay, thank you.
You are welcome. Great question. Thanks for clarifying. Okay. So if we then take our knowledge about writing balanced equations and we think about stoichiometry, we're going to have to write out a balanced equation in order to solve this problem. It gives us some information in the problem for how to do that. So it says 0.8 grams of sulfur is combusted to form SO2. So when I see the word combusted, I need to think about the fuel, right, as oxygen. So think for a moment about how you would write a balanced equation for sulfur plus oxygen going to form SO2. Okay, so let's take a look then at what this balanced equation would be. So this is really a problem that asks you to do several things. It's a combination problem of balanced equations and thinking about stoichiometry and thinking about thermochemistry. So my balanced equation is sulfur, the solid nonmetal, plus O2, the gas, goes to SO2, the gas. And so I get that from taking a look at this problem. So sulfur is my starting material. The word combusted tells me that there's oxygen involved. And I know that O2 is a diatomic molecule and that it's a gas. And then my product is SO2 gas. And if you're like, ooh, I'm not sure that I know that, that's okay. You could always look up, right, and check out to see what would be equations that would form SO2. And again, you're not limited, right, by the resources of just what you have available in your notes. If you have questions, you can always look at the OpenStax textbook, for example, or other online resources. Okay, so now we have our balanced equation. What do? Well, we need to think about the fact that this problem tells us some other pieces of information that's really going to help figure out what our next step is. So the keywords here are when the reaction takes place in a bomb calorimeter. Anytime you see the words bomb calorimeter, in your mind, you should hear all sorts of bells and whistles that tell you that this is a thermochemistry problem. Part of the challenge that we have as chemists and scientists is being able to think about what key concept we actually need to use in order to solve a problem. And when you see a keyword like this, it really sets you up for success because it tells you that you're going to want to use some type of heat transfer equation. Then we have to look really carefully at the information that's given. So it tells us the temperature of some mass of water increases by 17.8 Kelvin. This is really important because it says the temperature increases by, which means that this is actually our temperature change, right? Our delta T is already given to us. We don't have to figure out what our initial and final temperatures are. They've already given us our change T. So we've written our combustion reaction. Now we have to calculate the heat of combustion of 1 mole of sulfur. Now here's our dilemma. Our heat equation is going to give us units joules, but the problem is asking for the heat, right? And that's typically given in kilojoules per mole. So I have 2 steps then in this equation that I need to think about. So the first step is my heat transfer equation. So I'm going to look at the water and take the information that I'm given for water in order to solve. So I know that Q is equal to mass times my specific heat capacity of water times my delta T. Then I can substitute and solve my given. So I'm given 100 grams. I can look up the specific heat of water. Notice the units here matter. joules per gram Kelvin. I want to keep those units because the temperature change that I'm given is in Kelvin. And just as a passing note, you typically don't want to have to deal with negative temperatures in degrees Celsius, which is why keeping the units in Kelvin is most helpful for you. So I multiply everything through, and that gives me 7,450 joules. But I know that when I'm talking about heats of combustions or enthalpies, those are typically given in kilojoules. So I need to convert my joules to kilojoules. I'm going to do that by dividing by 1,000. Because I can divide by 1,000, I now can say that my answer is 7.45. Why is this negative sign there, right? Why do I have negative 7.45 kilojoules? Take a moment, think about what your answer would be, and give a reason why that charge might be negative in the chat box. What do you think? Why do we have a negative sign for our 7.45 kilojoules? Another way of asking that question. Ooh, thank you. Yes. Right? Because I am transferring heat. So in this case, my reaction is taking place in my bomb calorimeter, and the heat from the reaction is transferred to my water. And so if you think about it, the heat that exists in the reaction, right, as a result of its being contained within the calorimeter, is what then gets transferred to the water. And so in this case, right, I have a negative sign, and that tells me that heat is being given off. Okay, I'm not quite done though, because here's the thing. I know that my overall answer is asking for kilojoules per mole. That means that I need to calculate the moles of sulfur. So let's think about this. In 1 mole of sulfur, right, I have 32 grams. So I'm going to take my 0.8 grams of sulfur, divide by its molar mass, right? And that tells me the number of moles that I have. So if then I divide my kilojoules by my number of moles, then I have the amount in kilojoules per mole. So there are a couple of pieces of this problem that are really important that we want to be attentive to. The first piece, and this is probably the one that most folks get hung up on, right, is where do you start solving a problem like this? Well, it's always a good idea to start with a balanced equation. Rarely will you go wrong if you're starting with a balanced equation. Then it's a good idea to think about what are the givens in the problem. So what is the information that you have been given? And in this case, you've been given the mass of the water and the change in temperature of the water. And because you're savvy as a chemist, you know that you actually already have the value for your specific heat of water because it's given on your equation sheet, or because it's a constant, it's something you can look up. So now you're in a position to be able to solve this problem because you have all 3 of these variables with respect to water. Then the other piece of this problem that we don't want to forget about is this negative sign, because it tells us that heat is being given off. And if you're like, well, how do you know that heat's being given off? A combustion reaction is always going to give off heat. I want you to think about your favorite fireplace, right? Or your favorite campfire, right? Or your favorite source of combustion, whether that's a grill, right? Or some other appliance that gives off heat through combustion. Right? We always want to make sure that if we're giving off heat, that we're accounting for this negative sign because it's an exothermic reaction. And then the last piece of this problem that I think most folks actually on exam 2 did really well on is being able to calculate the amount in terms of moles of sulfur. So this is a problem that puts all of those pieces of information together. Now maybe you're thinking to yourself, okay, well that's great, but what are some of the things that we haven't talked about for a bit that I'm going to need to be able to do for this exam? So this example is a great model of a type of problem where there are many different ways you could ask a problem, and there are many examples that would illustrate that concept. So this was a problem that asked you to choose a metal and choose a strong acid. And then you're going to write a balanced equation. Oh, look, there's that balanced equation again between the metal solid and the acid. And then you're going to calculate the oxidation states for each atom. And you're going to determine which element is being oxidized and which element is being reduced. Part of what I hope you're starting to notice is that most of the exam questions are asking you to do more than one thing, which means there's a multi-step problems. That's pretty common when you start to think about the types of problems you're going to be solving in your subsequent classes. They're going to typically ask you to do more than one task. And part of your goal as a savvy scientist is to think about what are the possible tasks that you might have to do in order to be able to solve this type of problem. So let's look at an example of the different types of tasks that an oxidation reduction problem asks you to be attentive to. So the first thing is writing a balanced equation. And again, this is the space where we want to be careful, right? We're choosing a metal, and beautiful news here, we know that if we have a metal by itself, it's going to be a solid. Very rarely do we have metals that are liquids or metals that are gases. Those are really big exceptions. Almost always, if we have a metal by itself, it's going to be a solid. Here's the other piece of that that's also really beautiful. If we choose an acid, say for example, like H2SO4, we know that that's typically going to be aqueous because rarely do we have acids, even if they're strong acids, that are completely pure. If they are pure, sometimes they're referred to as glacial, but you likely aren't going to see those because they're really dangerous chemicals. Our strong acids that aren't aqueous solutions are incredibly strong. So we are typically always going to write our strong acids as aqueous. Now, we're not quite done yet because we've only been given the starting materials, which means we have to think about what our products would be. But here's the beauty of this type of reaction. A metal and a strong acid is always going to react to be able to evolve hydrogen gas. So one of the products you know you're always going to see is going to be H2 gas when you react a metal with a strong acid. Then it's up to us to make sense of, okay, well, what is the other product? In this case, the zinc is going to become the counter ion or the cation for our anion. And in this case, our anion is sulfate. So that's the first step of our reaction, is to think about our balanced equation. We might want to check to make sure it's balanced. So we have zinc on the left, we have one of those. We have one zinc on the right. We have one SO4 or sulfate on the left. We have one SO4 or sulfate on the right. You could separate those out and think about individual sulfurs and individual oxygens, but it's actually time saving for you to keep them together as a polyatomic ion. Then it's super useful to think about whether or not your hydrogens are balanced. Do you notice that's one of the things that we typically do last when we're balancing equations? We typically balance our oxygens and our hydrogens last. And in this case, they are balanced. We have 2 on the left, 2 on the right. So beautiful, I have a balanced equation. The next task that I'm being asked to do is to think about the oxidation states of my reactants and my products. Now, this is something where you actually have a resource that's available to you. If you recall, from exam 1, you had a handout that allowed you to determine the oxidation states based on oxidation state rules. Eventually, you're going to practice this to the point where you know those rules off the top of your head. In fact, I know that you're going to do that by the end of Chem 111. But for right now, if you're not completely familiar with what those oxidation state rules are, then I highly recommend that you find a resource, either from your notes or from online, that makes it easier for you to be able to assign the oxidation states. It's not something you have to memorize right now. It's more important that you're able to make sense of how to use those rules to assign oxidation states than that you just memorize them. So let's think about how we assign oxidation states. We know that any metal by itself, or any free element for that matter, is going to have an oxidation state of 0. So hooray, we know that we can already assign 0 to zinc because it's a metal by itself, and 0 to hydrogen because H2 is a diatomic gas. Again, that's an element by itself. So both of those are going to have oxidation states of 0. But now we have to think about how we assign oxidation states for our H2SO4 and for our zinc sulfate. In order to do that, we need to think about two things. One, hydrogen, unless it is paired with hydrogen in the form of peroxide, is always going to be +1. So the delightful news for you is that if you see a hydrogen, you should smile, because unless it's in the form H2 as a gas, its oxidation state is going to be +1, unless of course it's a peroxide. We also know that oxygen, right, has a very high priority in terms of its oxidation state. It's almost always going to be -2. So then we can use the information of 2 times +1 plus oxygen. We have 4 of those, so 4 times -2. So that means that I have -8 and a +2, which means that I have sulfur -6. But because my overall charge is 0, and I want to get sulfur by itself, it means that the oxidation state for sulfur is going to be +6. Now, that's math that you can probably do in your head, but if you wanted to write it out, that would be okay. It's not a problem to do that. You're going to notice, oh, how delightful, that in the case of zinc sulfate, we have a similar pairing. So we have oxygen, we have sulfur, and now we have zinc. But in this case, I don't know what zinc is, but I do know what sulfate is. And so I have to ask myself the question, is sulfate's oxidation state going to change? And the answer is no. So I can already assume that if I have SO4, right, the oxygen is still going to be -2, and the sulfur is still going to be +6. So because I know that, then the only atom that I need to solve for in terms of its oxidation state is going to be zinc. And so if I add those up, it's a very similar conundrum. I have a -8 and a +6, which means that zinc has to be a +2. So Mackenzie asked this really great question. Why does the oxidation state not change? Well, here's the beauty of this. So if you think about sulfate, right, as a polyatomic ion, right, the reason it's an ion is because it has a -2 charge. And if you were to draw the Lewis structure for sulfate, right, there's an optimum Lewis structure where the sulfur is in the middle and then it's surrounded by the oxygen atoms. The only time you're going to see an oxidation state change is if you're changing the number of electrons that belong to sulfate. Well, if sulfate still has a -2 charge, as it does on the left and as it does on the right, then that means that its oxidation state hasn't changed. So that's the reason why I can also infer that zinc has a +2 as its oxidation state, because zinc is the cation for sulfate. I know that sulfate has a -2 charge, which means that zinc has to have a +2 charge. And I know that for metal cations, their oxidation state is their charge. So in this case, zinc has a +2 charge as a complement to sulfate's -2 charge, which means that zinc has an oxidation state of +2 in this instance. Now, Mackenzie's question is really astute, because here's the other beautiful part about oxidation reduction problems. For at least the examples that we are looking at this semester, you are typically going to see one atom where it's gaining electrons and another atom that is losing electrons. We're going to look at that pairing, and so that means that if I'm looking at zinc, and I know that zinc is going from 0 to +2, that means that it is losing electrons. Now, you might be thinking to yourself, wait a minute, it says +2. Doesn't that mean something else? And the answer is no. Remember, +2 is the charge. So if zinc is getting a positive charge, that's because it's losing electrons. So zinc is what gets oxidized because it's going from 0 to +2, which means then that hydrogen, if it's going from +1 to 0, right, is reduced, because in this case, it's gaining electrons. So if its oxidation state is decreasing from +1 to 0, that means that it has gained electrons. This concept of oxidation and reduction is incredibly powerful in biology. Arguably, it's the reason why our cells function and how we transfer electrons, right, from the food that we eat to other cellular processes. It's part of how we make the energy that fuels our cells. And the really beautiful part about this oxidation and reduction process is that you can use it to drive other reactions. And so the power of this concept is that it's actually going to be something that we can use to make reactions that aren't particularly favorable run. So being able to identify oxidation states and being able to determine what is oxidized and what is reduced is a critical skill in chemistry. Let's look at another skill that we're building. You've probably seen several different types of gas law problems. This is one that was similar to what we saw in exam 2. And the critical piece for solving this problem was recognizing that you needed to do some conversions or some dimensional analysis to get the correct units. So we live in a world where you have multiple ways of representing information. So sometimes you're given information with the associated units, but those units aren't particularly helpful for solving the type of problem that you're working on. That's where we do unit conversion. So our ability, say for example, to convert between degrees Celsius and Kelvin is key. So let's think about how you would convert between degrees Celsius and Kelvin. Take a moment and make sure that you can do that. So part of what I want you to see here is that your first steps might be to take stock of the information that you're given in a problem. So when I'm reading this problem, I think to myself, okay, a helium-filled balloon. Okay, I think helium is a gas. Balloons certainly are filled with gas. At 22 degrees Celsius, okay, that's a temperature, is dropped into a large container of liquid nitrogen, another temperature. I'm given a final volume and another temperature. Okay, this means that I'm solving some type of problem associated with the gas laws. In order to be able to solve that problem, there are a couple of things that I have to be attentive to. The first is that I have this generic expression of PV over NT, and that's equal to R. If you're like, oh, I don't remember it that way, I always remember PV equals nRT. That's fine. You can rearrange that expression to get to this expression. The key is if you have a changing conditions gas law problem, the reason you can solve that problem is because you set your first set of conditions equal to your second set of conditions. And your units really matter. So in this case, the units for the gas law constant are atmospheres, liters per mole Kelvin, which means that anything that you're substituting in here needs to be in those units. Otherwise, the problem won't work. So we're going to convert to Kelvin for our initial temperature. We're going to convert to Kelvin for our second temperature. Note, this is some additional information that's not necessary to solve the problem. And then we're going to make sure that we have the other pieces of information from the problem, our 0.45 liters, and we're solving for V1. Now you might be thinking to yourself, okay, well, what about the pressure and what about the moles? Well, we're going to need to assume in order to solve this problem that our pressure and moles are constant. Sometimes you're also given information, say for example, that you have your reactants at standard temperature and pressure, and it's important that you know how to convert those to meaningful quantities. But in this case, we're going to make the assumption that our pressure and our amount of moles is constant. So we're going to be able to simplify this equation overall so that we're solving V1 over T1 equals V2 over T2. And then I'm going to rearrange this expression so I can solve or isolate for V1 by itself. The reason why that's so important is because I'm going to then substitute and solve, and I want to make sure that my units cancel so that I have the correct overall units for my problem. Notice, right, once I substitute, my kelvins cancel, and then if I multiply across the top and I divide by what's on the bottom, I get 1.41 liters. But as usual, I have to be attentive to the other information that's given in the problem. In this case, I have 2 sig figs. So that means that I need to rewrite my expression as 1.4 liters. So somebody asked, what does the R stand for? The R is the universal gas law constant. So if you look at your equation sheet, you're actually given several different values for R. Depending upon the type of problem that you're solving, you're going to want to choose the one that has the correct units. And in this case, because we're going to solve for temperature and volume, right, we're being attentive to using liters and Kelvin in our problem. So if you're like, I wonder, am I using the correct units? Sometimes one of the best ways to check your units is to think about whether or not there are any constants associated with the problem that you're solving. This is a great example of a problem that requires you to think about a given equation and then to rearrange that equation so that it is useful for you. Rarely are we ever just going to take an equation and plug in values mindlessly. What we actually want to do is be able to think about what is it that we're really looking for in this problem? How can I manipulate an equation so that I can isolate the variable that I'm looking for? And sometimes, right, there might be one or two steps where I have to solve an equation and then use the value from that equation to be able to solve the actual quantity that I'm being asked for in a problem. So let's take a look at an example that's like that. So here's a thermochemistry problem. It says the combustion of 4.086 grams of indium increased the temperature of a calorimeter by 1.626 degrees Celsius. The energy equivalent, or the amount of energy required to raise the temperature by 1 degree Celsius of the calorimeter, is 10.095 kilojoules. What is the heat evolved per mole of indium? This is a great example of a problem that you may not have actually seen one of before. It's giving you information and it's giving you units, and it's going to ask you to solve a problem by making sense of those units. How do we make sense of the units? Well, let's take a look at some of the key information that we're told in the problem. So we see the word calorimeter, which should tell us, right, even if we didn't have the large title of thermochemistry, that that's the type of problem that we're solving. They give us an amount in terms of grams, or the mass. They tell us the energy equivalent, or the amount of energy required to raise the temperature by 1 degree Celsius, and they give a value. And then they're asking us to figure out the amount of heat per mole. So let's think about the information that we do know. From the problem, we know that heat is an energy equivalent, some amount of energy that we've been given in the problem, multiplied by our change in temperature. So if I think about that, I'm given my energy equivalent, that's my 10.095 kilojoules. I know that it's my energy equivalent because of the units kilojoules. I'm also told in the problem that that's the amount of energy required by 1 degree Celsius. So this is kilojoules per degree Celsius. I'm also told what the change in temperature is. In this case, 1.626 degrees Celsius. So I need to multiply these two together so that my degrees Celsius cancel and I'm left with kilojoules. But the problem says, what is the heat evolved per mole? So this is where I have to read the problem very carefully, because the keywords per mole are telling me what it is I need in addition to solving for my heat. So now I need to solve for my moles, my 4.086 grams. I need to look on my periodic table and find the molar mass of indium. Once I've found that, I can calculate the number of moles of indium. Then my heat per mole is my 16.41 kilojoules from the first part of the problem, divided by my moles that I solved for in the second part of the problem. Notice, right, because of the word evolved, right, anything that is heat evolved means that I should have a negative sign here, because that's energy or heat being given off. So the sign is a really critical part of the solution to this problem. Now, you've probably been thinking, Well, we haven't ever solved a problem like this as an example in class before. And you're right, we haven't done a direct example that's just like this. But you have everything that you need to know in the problem in order to be able to solve this type of question. The most important part is that you pay particular attention to your units and that you are being attentive to what it is you're actually being asked to solve for. Let's take a look at another problem that requires us to make sense of new information. So here's a periodicity problem. When we studied quantum chemistry and then we looked at electron configurations, ultimately what we were thinking about are patterns in the periodic table and the way those patterns influence the structure and behavior of atoms or molecules that we might study. So let's think for a moment. Explain why ionization energy decreases for the noble gases as you move down the periodic table. If you're thinking to yourself, you're like, okay, maybe I need a periodic table for reference. If so, that's great. I highly recommend that you find one. Then you're taking a look at the diagram that we're being given here. So notice we've called out 3 noble gases. We have helium, we have neon, and we have argon. And if we're reading the table correctly, it looks like helium has an ionization energy in EV that's roughly 25, whereas neon has an ionization energy that's between 20 and 25, so let's say 22. And then argon has an ionization energy in EV that's slightly above 15, so maybe we can say 16. So the first thing that this problem asks you to do is to observe what the trend is. And in this case, you could visualize that simply by looking at the diagram and seeing that the ionization energy decreases as you go from helium to neon to argon. Or you could analyze the diagram and actually call out the numbers and then make that inference. Now, the question asks you why. So it's not just asking you to identify the trend, but to provide an explanation why. So elements on the right of the periodic table have a tendency to have higher ionization energy. That's because they have more electrons, and the more electrons they have, the greater the separation between the electrons and the nucleus, or more specifically, nuclear charge, that positive pull of the protons on the electrons. Notice that noble gases have completely filled valence shells. So in this case, each one of these atoms is going to have a completely filled valence shell. So we can't make an argument based on valence electrons, but we can make an argument based on electron shielding. So electron shielding is when there are more electrons between the positive charge of the nucleus and the outermost electrons. So in this case, helium, right, has very few electrons between the nucleus and the outermost shell. In fact, there are none. Helium has only one subshell, the first subshell, which holds 2 electrons. So those 2 electrons are close to the nuclear charge at all times. If we think then about neon, right, neon has 2 subshells. The first subshell, which holds 2 electrons, and the second subshell, which holds 8 electrons. So there are only 2 electrons between the outermost, or the valence electrons of neon, those 8 in the second subshell, and the nucleus. There's only 2 electrons that are shielding the nucleus, or that positive charge that's pulling on those electrons. But if you compare that with argon, argon now has the first shell, which has 2 electrons, the second shell, which has 8 electrons, and then the third, or the outermost shell, which has 8 electrons as well. Now there are 8 electrons between those outermost electrons and the first subshell and the nucleus. So there's a lot more electrons that are shielding or protecting those outermost valence electrons from the positive charge or the pull of the nucleus. The reason why we want to be attentive to thinking about periodic charge or sorry, periodicity and nuclear charge, maybe that's a better way to say that, is because it's really the pull of the nucleus that holds those electrons to an atom. So the farther away electrons are, the easier it is to be able to pull them off. And the first ionization energy is how much energy do I have to put in to pull off an electron? So being able to explain periodic trends is something that's going to be really helpful for you as you move forward when you start to think about especially reactivity and the role that electrons play in forming and breaking bonds. One more review that is really critical is thinking about electron configuration and ions. This is something that we've talked about. Ooh, Heba had a good question. Before we move on, I'm going to answer Heba's question and say, yes, it's definitely related to electron size. And really, electron size is all about the number of electrons. Right? So your atomic size is governed by atomic number, which is the number of electrons and protons. So yes, it's a great observation, Heba. Great question. So if you used atomic size in your reasoning, that would be perfectly valid as a response, which I think brings up a really good point. So let me go back to this for just a moment. I had somebody ask me the other day, which I thought was really awesome. Are there like magic words? And the answer is no, right? The goal behind a claim evidence reasoning statement is that you make a claim, you cite evidence, and that the reasoning that you use makes sense, which means that there are actually multiple ways that you could answer this question and have it be correct. If you're like, but what if I answer it wrong? Well, then you have the opportunity to revise your thinking, or, right, hopefully you receive feedback where I say, okay, I understand why you wrote it this way, but this is additional information that's going to refine your answer, and then you iterate your response and improve it. That's really what we do as scientists every day, is that sometimes, right, what we think we know about a phenomenon is actually something that we then have to revisit because additional evidence shows us something else. That's very common in the practice of scientists. So we get used to that by thinking iteratively and being willing to evaluate or consider new evidence in light of our current thinking and then make changes when necessary. So don't ever be afraid to revisit what you thought about something else. I have to do that all the time. And I would say that if I think about the amount of time I've spent thinking about chemistry, I've spent a lot of time thinking about chemistry. But the fact that I need to revisit my thinking on a daily basis is actually a beautiful and really exciting thing, because it means that I'm always learning and I never run out, right, of new ideas or refining ideas to think about, which means that there's always something new to explore and discover, which is beautiful. This is why we love chemistry. Okay. Electron configurations. Here's part of what I want you to think about. We typically train to be able to identify the electron configurations for atoms in a periodic table. But what happens if I need the ion of that atom? So what happens when I'm losing electrons? What do I do with my electron configuration then? Iron is a really good example for us to consider. So if I think about the iron atom, there are two pieces of information that I think you want to be attentive to. One is the order of filling electrons. Now, if you're like, ooh, I don't know that I remember that, there's a really great trick or tip. You can go back and look at the virtual learning plan. And in that virtual learning plan, there's a video that helps review the order of filling atomic orbitals. But essentially, the way it's currently written is the order that I fill. I fill the 1s2 first, then the 2s2, then 2p6, then 3s2, then 3p6, then 4s2, and only then do I fill 3d6. But the way we typically write our electron configurations is that we group our principal quantum numbers together. So there's only one principal quantum number 1 here. I group my 2's together, I group my 3's together, and then I write my 4's. So that's the way that we typically write our electron configurations. And that's super helpful because 4s2 is the slightly higher energy level that I'm going to pull my electrons from. So when I form an Fe2 plus ion, I'm going to take those electrons not from 3d6, but instead I'm going to pull them from 4s2. So I'm going to take those 2 electrons away, which means now that that 4s orbital is empty. Because it's empty, we don't write it. So now my Fe2 plus ion would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. Now some of you might be wondering, but wait a minute, Sloan. I know that Fe can also form the 3 plus ion. What happens then? Well, I take my electrons still from 4s2, those are 2 electrons, and then I take my 3rd electron from 3d6, so it becomes 3d5. The reason why it's common to see Fe3 plus is because 3d5 is a half-filled d orbital. So that's a pretty stable orbital, which is why we commonly see Fe3 plus. So you're going to want to practice writing electron configurations for ions, both cations and anions, based on information available from the periodic table. Now, just so that everyone's really clear, I sent you a periodic table that includes the electron configurations of all atoms. Now, granted, it is written in really tiny text, so you might need to zoom in to be able to see it. But if ever you're in doubt and you're not sure what the electron configuration is of the atom that you're starting with, you can always reference that in the periodic table. Hopefully, you can also explain why we fill the orbitals the way that we do. Okay, let's talk a little bit about phase changes. So this is where we left off. We were talking about phase changes for the Clausius, Clapeyron, and other types of problems associated with chapter 10. And so part of what we want to think about, right, is changes in energy with respect to phases. So here's our question. How much heat must be added to raise a sample of 100 grams of water at 270 Kelvin to 280 Kelvin? The specific heat capacity of water is 4.180 joules per gram Kelvin, and water's heat of fusion is 335 joules per gram. Now you might be reading this problem and thinking, they want me to do what? What is it that I'm doing? Here's the key. What is the temperature at which ice melts? Think about that and answer in the chat. What's the temperature at which ice melts? What do you think? Ice typically melts at what? So 100 degrees Celsius is the temperature at which water boils, right? Maybe if I said it another way, you would, right? When does water freeze? When does water freeze? 32, what's the units? Thank you, Stella. Thank you, Heba. So at 0 degrees Celsius, 32 degrees Fahrenheit, okay, at 0 degrees Celsius, what is that temperature in Kelvin? Hopefully, you know that in order to get to Kelvin, you're going to add 273 to whatever temperature you're given in degrees Celsius. So that means that water in the ice form melts to form liquid water at 273 Kelvin. So this is a problem where I'm starting with solid ice and I'm melting to become liquid ice. So when I think about this temperature change, right, I'm actually going between 2 phases. I have my solid phase of ice and I have my liquid phase of water. So if I'm thinking about this problem, then I'm going to need to figure out the amount of energy that it takes to warm liquid water, and I'm going to need to think about the amount of energy that it takes to melt ice to form that liquid water. So this is a really great example of a two-step phase change problem. The first part of solving this problem should look pretty familiar to you. It's using my heat transfer equation. So Q is equal to my mass times my specific heat times my change in temperature. The second part of the problem is my mass times my delta H fusion. So this is the enthalpy of fusion, or the energy that it takes to melt ice to become water. If I think about the information that I'm given in the problem, I'm given my mass in grams, I'm given my specific heat, and I'm given my delta T. So when my water melts to form liquid water, my liquid water warms from 273 Kelvin up to 280. So I'm going to look at my temperature change that's given overall. Okay, so I have 280 minus 270. That's my total temperature change of 10 Kelvin. So the first part of this problem is substituting in what's known, my mass, my specific heat, and my temperature change. And then the next part of the problem is my mass times the other piece of information that I'm given in the problem, which is the heat of fusion, so 335 joules per gram. So if I think about solving this problem, then I'm thinking about the phase change of both ice melting and water warming.
Dr. Corinne?
Yep.
I didn't get why are we adding the water's heat of fusion? We can just find the energy by multiplying M times the heat capacity times the delta T, but I don't understand why we're adding the heat of fusion.
It's a great question. That's because there's additional energy whenever we have a phase change. A good way to think about that is that a phase change actually represents reordering molecules. And so if you're thinking about that, say for example, you're reordering the objects in your kitchen, you're going to expend energy to move those objects around. And so that's why you have to include the additional term of the heat of fusion, because there's energy that's involved when you change the arrangement of molecules of water that you see in ice to molecules of water as they exist in liquid. And so if we think about that, here's a good example. Hopefully you should be able to see that if we're thinking about, say for example, solid, right? The structure of solid water is very ordered. Right? In fact, it's almost a lattice framework. Whereas if I compare that to liquid water, it's much more jumbled. And if I'm comparing that to gaseous water, it's completely separate. So if we go back then to think about this problem, Heba's question is an astute one. It means that we have to use the energy of warming in addition to the energy of changing its phase or its state. So one of the other pieces that you're thinking about, that's a great question. So yes, this is thermochemistry and its phase changes. What you're going to recognize is that almost everything that we study in terms of changing phases is intimately tied to thermochemistry. So take a minute and think about the structure or the setup of this problem. And then the next thing we'll talk about, I know that lots of folks have questions about the structure of the exam, so I'm going to walk you through that next. But this is a really important problem because I know it's going to show up for both exam 3 as well as showing up on your final exam. So you're going to want to make sure that you're attentive to phase changes because it's something that you potentially are going to have to solve, right, on both of the assessments coming up. So notice units here are joules, right? That's because I'm talking about the heat that I'm transferring. And again, I want to be attentive to sig figs. Okay. So with that, we're going to do two things, and then we'll be able to talk about the exam. So here is the first thing that we're going to talk about. In Thursday's discussion this week, we're going to be looking at examples of phase change problems that are going to show up on the final exam. So chapter 10 problems were the last chapter that we covered, and we haven't really done a lot of practice yet with Clausius-Clapeyron and or heating curve, so I want to make sure you have the chance to practice that. That's the goal for Thursday's discussion. Wednesday, we don't have class because you need that 2-hour time block, whenever you're choosing to take it, to be able to work on your exam. And so to be fair to you and make sure that we're using our time wisely, we will not have class on Wednesday. That doesn't mean you have to work the problems on the exam during that time period. It's just making sure that you have the time to be able to sign up and take that exam. So if you're doing that at some other point in time, then you can still have time to do work for this class or other classes. Okay, last piece that we're going to talk about, before we get to the last 5 minutes of class, I want to talk about two things that are really important. So the first is, if we are thinking about the key for the practice exam, I noticed that for some reason it had scanned the second page twice as opposed to the first page. I think that was just an error in the scanner that I was using, or it could have been user error on my part. I've fixed that, so the key is now up. Ali had made the suggestion that I do a separate PDF document of common errors, and so I have included that as well. And then the other piece that I want you to be able to see is the rubric that we're going to be using. So I've attached that to the email. You already have access to this rubric. This is how I score you. Notice, right, each of these, right, you have a total of 5 possible overall points per segment, right? And I'm scoring, right? So typically, right, defining the problem is something that I have done for you, and then you're using that information to do each of these 4 things. So defining the problem is something that we've typically already done based on the language or the information that's in the problem. So that's something that when I ask you questions, I will really be asking about these last 4 components. So identify strategies, proposing solutions, implementing the solution, and then evaluating the outcomes. So this is the rubric that I use to score you. You have 5 possible points. This becomes 4, this becomes 3, this becomes 2. And then if you don't have anything in terms of your response for that, then it would be 0 points. But you all are super savvy and astute. So my expectation is that you will be very successful at being able to talk me through your process of how you solve these problems. The other piece that I think is really important for you to be attentive to is the following. So if you're thinking about, right, resources that are available to you, those are here, right? So you can use your molecular geometry reference sheet. I would expect you to be able to use that on the exam. I also expect you to be able to use your periodic table. Again, this is not a resource limited exam. The intention is that you understand the process that you use to solve these problems, and that you can walk me through it. Now you might be thinking to yourself, well, wait a minute, Corin, that's great, but how do I know what type of problem you're going to ask me about? Well, I thought this would be a really great way to represent the information. These are the big ideas that exist in chemistry. So the idea that chemical elements are the building blocks of matter, and that you can understand those in terms of the way that atoms are arranged. The second big idea is that the chemical and physical properties of materials can actually be explained by their structure, by the arrangement of atoms, ions, or molecules, and then the forces that exist between them. That any changes in matter are going to involve some type of rearrangement and or reorganization of the atoms, or the transfer of electrons. And then that the rates of chemical reactions are going to be determined by the details of the way those molecules collide. So these aren't static, they move. And it's the way that they move that changes how they react with each other. And then you're going to notice that the laws of thermodynamics are really essential in describing the role of energy, and that helps us to explain and predict changes in matter. That includes things like changes in the states of matter or the phases of matter. And then the last big idea is that bonds or attractions, they can be both formed and broken, and that those two processes are in constant competition, whether I'm forming a bond or breaking a bond, and they're going to be sensitive to my initial conditions and then to any external forces or changes. So the reason why I wanted to share this with you is because I feel like it's really easy sometimes to get lost in the weeds, but sometimes it helps if you pull back and think about the big ideas. Okay, last couple of pieces. So folks were like, hey, wait a minute, if we don't have class on Wednesday, how are you gonna score our quiz? Well, remember, your quiz is your exam reflection. So once you're done with exam 3, there's a link to this exam reflection that is in the email that you received from me today. You're gonna complete this exam 3 reflection, and it's a quiz score. If you are like, wait a minute, okay, Corin, I'm all ready to take this exam 3, but I just don't understand the process. Let me give you an overview of what that's going to look like. So let's say you signed up for Tuesday at 10 p.m., right? So this is Corin. I would send out the exam to you at midnight Monday night. You're also going to receive a calendar link from me. That calendar link will contain the Zoom URL that you would click. So at some point in time during the day on Tuesday, then I would set aside time, usually at least 2 hours, to be able to work on the exam. I would solve all of the problems on the exam, and then, right, I'm ready to be able to log on to Zoom and have a conversation about the process of how I solved a problem. And you're like, well, how do I know what problem you're going to ask about? Well, that's the part where it's random. I have a random number generator, and I pull a random number by clicking enter. It pops up a number, and that's the number that I ask you to tell me about. So your best, right, opportunity is to make sure that you've solved all of those problems to the best of your ability. That way you're positioned to be able to answer questions about any of them. So I'm going to hang out here, and if there are